Hello again. Today we're going to look a little bit deeper into current, charge, and voltage. The first thing I want to talk about is the direction that current might flow through a circuit element. In order to do this, I'm going to introduce a graphical representation of a generic circuit element that I'm going to be using quite a bit throughout this first chapter worth of videos. And the way that I draw a circuit element in general is to say that I have this is how I might draw a circuit element. And I'm going to label, these are called my terminals. And I might label them A and B. Very, very common to label them just A and B, just so that I can have a discussion about the different terminals and the different, where the voltages are developing. Generally speaking, I might write an arrow like this. And this is my current. So what I'm really saying is current flows into A and out of B. And that's important to notice, that the current is going into A, the same current is going out of B. Current is made up of electrons. I can't just create or destroy any of them. So if current enters an element, then a current must leave, and the same number of electrons into an element must go out. However, you might have an issue saying, well, what happens if the electrons are actually flowing the other way? What if my current is in fact entering at B and leaving at A? If that happens, all that it means is that I have essentially a negative current rather than a positive current. So what will happen there, as we're doing more examples, we'll see what happens, is that our currents come out to be negative. And that's okay. What it means is we drew the arrow the wrong way, and all we need to do is draw the arrow the other way and flip the sign. Since we don't know before we work on a problem which direction the current is flowing in, typically we just make an assumption, and we say it's going, in my case here I chose to enter at A and leave at B. You may have chosen something different. When we're done the analysis, we've come up with all of our numbers for what the currents are. What may happen is we find that some of them are negative. That being the case, all we need to do is flip our direction arrows and flip our signs. So don't worry too much about which way to know which way it's going. You can always just change it afterwards. So if current is going in and out, and current is the derivative of charge, we might want to know how much charge has actually been accumulated or flowed through that circuit. If you recall, the current, I of t, is the derivative of Q of t, where Q is the charge, by dt. So, going backwards, we might say that Q of t is the integral. And normally what we say in this course is from some time 0 up to some time Q of t dt plus Q of t0. So this might be a little bit different than you're used to from calculus because we have what we might call a definite integral here. We shouldn't have this constant of integration. In fact, the reason that this is here is because we are saying, well, charge can accumulate, right? Charge is made of electrons. Electrons can be stored in one place or another. So we might not be starting from 0. Very often what happens is we say, okay, well, Q of t0 is equal to 0, or it's equal to a constant. But just be aware that it is there, and that we might encounter this, especially in the textbook and especially during some of the practice problems, where your initial charge is non-zero and you still have to integrate the current. Oh, my apologies. That should not be Q of t. That is, in fact, the current I of t. Sorry about that. So let's do a quick example. So let us now suppose I of t is equal to 7t plus 3. And I now need to give some additional information here. It's not sufficient for me to just say, here's my current, let's integrate it. I need to know my initial time. I would like to know my final time. And I'd also like to know my initial charge. So I'm going to make life a little bit easier and say that t0 is equal to 0. So we're starting at 0. we're going to just assume that Q of 0 is equal to 8 coulombs. This is 0 seconds. We need to make sure that our units are correct and consistent. And now we want to know what is Q of 4, so Q after 4 seconds. Plugging it into my equation, if you recall, Q of t is equal to the integral from t0 to t, I of t dt plus Q of t0. I now plug in the things that I know. The integral from 0 to 4. I of t was given as 7t plus 3 plus Q0, which was given as 8. If I carry out this integration, what I will end up with is 70 coulombs. So that's how you go backwards from a current to a charge. This will become relevant where we're storing charge and trying to move it around, and specifically the component that does this is called a capacitor. We'll get to capacitor somewhere in the middle of the course, but I wanted you to be aware that there is in fact a reason that we might be considering the charge from the current. Alright, so the final thing that I'd like to do in this video is talk a little bit about how we quantify energy transfer. What that means is how do we measure how much energy has been transferred into or out of the charge. What this will do is set us up nicely for the next video where we're going to ask ourselves whether or not the charge is absorbing energy or delivering energy to a load or from a source. To do this, to quantify the amount of energy that is transferred, we talk about a quantity known as voltage. And like in the last video where we developed several new units, we're going to develop another one here called the volt. The key idea here is as follows. Charges gain and lose energy. And I'm using the shorthand NRG for energy as they travel through a circuit. If you recall, the unit of energy is the joule, or J, and the unit of charge is the coulomb, C. What we're interested in is how many joules are provided or removed from a coulomb of charge. So we need to know joules per coulomb. Energy transfer of 1 joule per coulomb is equal to 1 volt. That is the definition of the volt. If a coulomb of charge gains 1 joule as it moves through a circuit, it has moved through a difference of 1 volt, or has gained an energy difference of 1 volt. In the next video, we're going to be talking about how we can use voltage to actually determine how much power and how much energy are being transferred around the circuit. That's it for now.